Hi everyone. In the last few lectures you have learned about the power of randomness for all kinds of computational tasks, in particular sketching and streaming. Today, in this lecture, we're also going to demonstrate the power of randomness to yet another task, a fairly basic one, which is to build dictionaries. So I will define the problem of building a dictionary, and then we'll see how randomness helps us solve it. So, the subject of today's lecture is dictionaries via hashing. The randomness will to this technique of hashing that I will explain shortly. So the problem statement is as follows. So we're given some number of n key value pairs. So key 1, value 1, up to key n, value n. We want to construct a data structure, let's say D, such that, or rather, that supports search queries on the key value pairs. So what is a search query? Let's define it. So you pass the data structure to the function search, and you say, here's a key. Could you please tell me either the value associated to the key, if the key was part of the was in the list. So if the key that you're passing was one of those that was kind of from which the data structure was built, then you're supposed to obtain the value. Otherwise, you get some symbol that says nothing to return, because the key that you gave me is not among the keys from which data structure was built. Okay, this is just a search query. You have a bunch of key value pairs, put them in data structure, and later you want to query, here's the key. Could you please give me the value for it in case it is one of the keys? Now, search queries are the most basic ones, and they're the subject, they're indeed what we're discussing today. The techniques that we will discuss sometimes also extend to other types of queries. So you may want to insert in the data structure D a new key value pair, for instance, because it just came up later. You may want to delete a key and the corresponding value, and possibly other types of simple queries. The focus today is specifically on this, let's call it static regime, where we are given a set of key value pairs, and we only want to support search queries on it. This clearly, inserting and deleting queries is more this dynamic setting where your underlying set of key value pairs changes over time, and you want your data structure to adapt. Okay. In this case, the data structure itself would be a kind of a mutable input to the function that reflects the change. Okay, so today only static, so I'll just put a cross here that we don't consider it. Another important assumption is that we're going to assume that all these keys are distinct. Okay. For each key, there is only one value. Now, what efficiency concerns do we have in mind for solving this problem? So we have two. One is the size of the data structure. So we want to minimize the size of the data structure relative to the number of key value pairs. Now, we probably expect, and just because this data structure is storing n things, we do expect that the size of the data structure is going to be at least n. But ideally, it should not be much more than that, right? And we also want to minimize a running time of a search because that's the query that we want to support. Okay, so that's the problem we want to solve today. So let's think about what we might do. So an immediate proposal could be the following. So idea, say number one. We could just say, you know what, just sort the list of key value pairs and just let the data structure be the sorted list. So let B be the sorting of sort by key, not by value. Let's say sort by key the list and call that the data structure. Then, when you search the data structure for a particular key, you're going to binary search for k. If you find the key, return its value. Because because the list has been sorted by binary searching, you will either find something or nothing. If you find something, you will return its value. If not, we can return that we didn't find it. So let's see how this basic solution compares, or how does it do with respect to the size of the data structure and the time to search. So the size of the data structure really is just n, right? So it's kind of optimal. Here I'm just discounting the bit size of the key and the value. We have like n things inside it. And of course, if the keys are fat, then this will be fat by some multiplicative factor to that. The time to search is going to be order of log n, right? Because we have a sorted list of n elements. We're looking for an element. And in the worst case, we're going to have to make log n comparisons between keys before we are able to answer the search query. So this is really not bad, okay? This kind of initial idea, it's really not bad. But today we're going to be greedy, and we are actually want to do even better than binary search. And specifically, we want to our goal will be to reduce search time to constant, which seems kind of almost paradoxical. How could you reduce it to constant, possibly even in the worst case? So maybe to give some intuition for why constant is not so crazy, let's look at a different idea that actually sacrifices space, but will give you worst case constant time. And then we'll see how we can use hashing actually to reconcile and get the best of both worlds, both good time and good space. Okay, so sorting gives us logarithmic time for search and linear space. So another idea would be to say, okay, let's set D to be an enormous array of all possible keys, not just the ones that we have here, but the keys come from some universe. Maybe let's write it here, that each ki is from some universe U. Okay? So this is an array of all possible keys, and you store at location k the value for it. If any. Okay, so more mathematically, basically d is now a function from u to those values, such that d of ki, we set it to be vi, and d of elsewhere, everything else, we set it to be nothing. All right? When we do this, now the search of a key is a constant time operation. We just the kth entry of this enormous array, like you just go into memory at location k and return that value. Okay? So what we get here is that the size of D is the size of the universe. Okay? And the search time the time of search is order 1. It's like one lookup. Okay? So basically, by giving ourselves more space and interpreting the key as an address in memory, we could make sure that we are answering queries in worst case constant time. However, now we have this enormous array in memory. This is much, much more than n. In fact, it could be really exponential in n. You can think about it, right? So just maybe one way to appreciate it, suppose each of these keys are, 64-bit values. They are maybe, some IP addresses or something like that. This would be tantamount to saying, let's write down an array with all possible IP addresses. That's clearly like something that is not polynomial. But yet, there is some intuition here that is quite interesting. It says, you want to avoid binary search, just have some way to look up, to associate a piece of an array with a key. Here we're being a bit not very good with space because most of this array is not used. So somehow we would like to kind of compress this array down to just something on the order of n. Okay? If only we could have a way to re-index and just say, well, let's associate k1 to location 1, k2 to location 2, and k3 to location 3. And we could remember that. Then we could just look them up and say, OK, let's just, I know k1 goes to location 1, so I'll just go and check it. But how do I construct this mapping? So this is where the idea of a hash function comes in. OK? So now we start moving in the direction of using hashing. But to summarize, these are two reasonable ideas. Binary search has kind of bad, relatively bad search time, but good space. And this array idea of associating addresses, keys with addresses, has large space and very good search time. So the new idea is to rely on a hash function to map a small number of keys. Small number is like n, as opposed to all keys, to a small address space. So that we can allocate an array, it's just not going to be that big. So we're going to so out of all the possible keys in the universe U, we are only interested in a small number of them. Here's K1, here's K2, here's K3, up to Kn. There's only n keys we really care about. And we're going to apply a hash function which maps any key to a small array of size m, which we can view this way as buckets or slots, right? That's slot 1, slot 2, slot 3, up to slot m. And each of these keys will fall into some bucket. Okay? Now, it could be that some keys end up in the same bucket. So we're going to put a linked list to store information about all the keys that end up in the same bucket. So here it says there are 2 keys that ended up in bucket 1. There are 3 keys that ended up in bucket 2. And so on and so forth, right? So this is like an idea that we don't know yet what the hash function is. But if we do this, then the cost to answer a search the k to the number of keys in bucket h of k, right? Because when you're wondering, is k part of the list, and if so, what is its value? You evaluate h at k, you end up in one of the buckets, and you just have to travel and see, okay, is it this one? Is it this one? Is it this one? If at some point you find it, you return the value. Otherwise, if you continue through the whole list, then your answer must be no, because it must have been one of these, because you constructed the data structure to be such. So the goal now is that we want to find a sort of cheap hash function h such that there are few collisions for k1 through kn. Because what is there? These are, h of ki all appear somewhere here. Okay? So this is a paradigm. We're going to think of data structures that look like this. This you can think of h as basically translating, compactifying this idea and saying, let's not use directly the key as an address, but I'm going to translate the key into an address. And I want this translation to be evenly distributed. I want to pick m to be on the order of n so that most keys have very few collisions. Okay? Or all keys have very, very few collisions. So now we are really only left to think about what types of hash functions would achieve this goal. So here's an attempt. It's a bit of a silly attempt, but at least we understand what we should think about. One idea would be to say h of k would be the first log m bits of k. Meaning that, look, if I have to index into an address of m slots, why not just interpret the first log m bits of k as this address, right? It will tell me which of the buckets is going to go in. But this doesn't really make sense, does it, right? I mean, it might work for collections of n keys where such that their first log n bits are evenly distributed between them. But for all I know, all of the n keys start with the first log n bits. Okay? So the problem, maybe all of k1 through kn start with the same log n bits. And that's a problem because then they would all map to the first, say, to a particular bucket. And then when I'm running my search query, I have to travel it linearly. It's going to cost me order of n to answer it, which is much worse even than binary search. So it's maybe not a good choice of hash function. So maybe we should pick a different hash function. But there's there is a bit of some more of a fundamental problem here, that in some sense, no matter which hash function I pick, there are always bad choices of keys. So specifically, for any fixed h from u to m, actually, there exists some kind of bad choice of keys in the universe that make h map all of these keys to the same bucket. That's definitely bad, as long as the universe is like moderately large, which is always the case. Let's say greater than n-1 times m. This is like really a small universe. And the proof is like pretty simple, that by contradiction, that if this is not the case, okay, if all buckets have at most n-1 keys, then the universe can only be at most of size n-1 times m. Okay? Namely, if there is no bucket that if you were to hash all the keys in the universe were to contain n keys or more, in which case we could just pick those to be the bad ones, then the universe cannot really be n-1 times m, right? Because every bucket would have at most n-1 keys. So this is saying that no matter which hash function I write down, it's not just the first log n bits or the third log n bits or maybe something more complicated. Just the mere fact that I'm shrinking and I'm saying my output is much smaller, my output domain is much smaller than my input domain, means that I can always find these like bad collisions, okay, that are going to thwart my attempt here. And I really want this to work for every choice of keys, right? We want to construct a dictionary that has good behavior, no matter which key value pairs I'm starting at the very beginning. Okay, but we're in a section of the course that is about randomness. So the idea to kind of get oneself unstuck here is to pick h at random from some class of hash functions independently of the keys. So namely, the keys came up, and maybe they were. But now, after the keys have been fixed, you pick a hash function at random from a family in a certain way. And the family will be chosen to have properties so that no matter what keys showed up, with high probability over the choice of hash function of collisions, or lack thereof. So here the idea is to use randomness. Specifically, pick h at random from a family H, and this is independently from keys k1 through kn. Okay, so this is a worst case choice, but then after it's fixed, we pick H at random. Now, what is this family? So I'm going to write down here the property that is going to be important for us. Okay, it's a very fundamental notion in theoretical computer science. You can do many things with these types of hash functions, not just dictionaries. So we're going to say that H is universal if for every distinct pair of keys in the universe, the probability that H sampled from this hash function maps the two keys to the same bucket is at most 1 over the number of buckets. Okay? So this is the property that we're going to, the property and the only property we're going to use from this hash function. Okay? These are called the universal family of hash functions. This is also called pairwise independence. And now what I want to prove is that with this, if you pick H at random from this family, then in expectation, each bucket will have a constant number of collisions. Okay? So I'm going to prove that. I will remove this one, delete it, and prove it here. All right. The claim is that, so the technical claim that we're going to prove is that for every I in N, the expected number of collisions, rather, the expected number of keys in same bucket as ki is at most n over m. Okay? So this is saying, I'm going to take the perspective of the key ki. It maps somewhere. Wherever it maps, we are interested to understand how many other keys map to the very same place. And here, that in expectation, that number is n over m. Okay? So let's look at the proof. So let's define an indicator. Indicator I, no, not I, let me call it C for collision. C sub I comma j, or actually I have fixed I, so I'm going to use j and k. So Cjk is the indicator that says 1 if H of kj maps, if kj maps to the same bucket as kk, damn it. So instead of k, I'll say j, l. And 0 if the jth key and the lth key do not collide. Okay, so that's an indicator. The expectation that I'm looking for is the expectation of a sum for j not equal to I of Cij, right? This expectation here that I'm computing is exactly this quantity over here, because I'm saying pay attention to I. let's see in expectation how many other j's will collide with I. Okay? So by linearity of expectation, this is the same as putting the sum outside. So this is the equation for Cij. But what is Cij? Because all the keys are distinct, this is exactly this probability, right? So this is an indicator variable. The probability that Cjl equals 1 is exactly a probability that over a random choice of h, the distinct keys kj, but because h is universal, this quantity is 1 over m. So this is sum from j not equal to I of 1 over m. But how many j's are there? There's n minus 1. Okay? So that is the quant, and this proves that one over there. So if we take the number of buckets to be linear in n, okay? So let's say, think about it like it's something 10n, then each key maps to a bucket that in expectation contains order of 1, or rather order of, contains at most n over m, which is order of 1 other keys. This means that D, the size of data structure, which is m, is order of n, and also the time for search is order of 1 in expectation. This is not quite worst case time, but we've made progress. Okay? So again, because h is chosen at random, no matter what the keys are, because of this property, in expectation, every bucket contains an expected constant number of collisions. Now, and of course, this is just a random variable. Doesn't mean that all buckets will contain always a constant number of collisions, but in expectation, they will. Now, some of them may take more, but it does mean that the time to search is a constant expectation. And the size is linear period. That's a worst case choice, right? Because we fixed m. Okay, so that's progress. Now we have two questions here. Where do these hash functions come from? So we're going to talk about this now. And later, we're going to look at, it's kind of a bit unsatisfactory how the, like it's really unclear that we've done better than say binary search, because now we have this expected constant time, which is not very nice, right? It really, the fact that a random variable has a expected constant value doesn't really tell us a whole lot about it, okay? We want to have worst case guarantees. So let's now maybe do an interlude about where do universal hash functions come from. And we're going to sort of this very simple and efficient construction of these objects. All right, constructing universal hash functions. By the name universal at this point should be clear, right? That it means that it works for all keys. So an attempt could be to say, you know what, just H is a kind of completely random function from U to M. Okay, this will satisfy that property, but kind of the problem is that I mean, the description of H is going to be a random function. It means that for every key, you assign IID a slot, and you remember that choice as part of H. Okay, but this means that our data structure, which in particular contains the description of a hash function, is going to be like as large as our array. So we haven't really made any progress. So this is exponentially large. And the idea is to basically use inner products. Inner products have an important role they play in the area of so-called pseudo-randomness. This notion of universal hash functions is one of the basic notions in the field of pseudo-randomness. And inner products have many nice properties. Being universal hash functions is one of them. So let me make this concrete. Let's define the hash function. So we're going to make some sort of simplifying assumptions on the parameters. These come without loss of generality. So the number of buckets. If not, take the next prime. Like, it's okay. Like, if m is not a prime, just make it a little bit larger. And this will not change your asymptotics. We're also going to assume that the size of the universe of keys is a power of m. Okay. So once you fix your prime, just view the universe as some power of that prime. Again, if it's not, just make the universe a little bit bigger. It's not going to matter. And now we can view a key in the universe in base m. Okay, so it's just a vector k1 through kr, where kind of each ki, like k1 through kr is overloaded. So these are components of one key, and each component ki is between 0 and strictly less than m. Okay, we're just viewing the key, which comes from a universe m to the r in base m, right? So that gives you r components. So now we have the definition of the family. So the family H is going to be all hash functions that are indexed by elements of U. Okay, and HA of k is just the inner product of A and k modulo m. To write it explicitly, you just take over the integers A1 A component times K1 component all the way up, and you sum up all the kind of pairwise, component-wise products of the two vectors, and you take this one modulo m. That's a prime. All right, so a key comes from the universe. You can interpret it as a vector of r components. The hash function is described also by itself a key, right? So the way you sample a hash function is you sample a key. And the way you value the hash function is take the inner product of the description of the hash function and the key that you received as input. And what is the inner product is this one. You have r entries in each of the two vectors. You multiply them component-wise and you add them up. And then you take the modulo m. So this is the hash family one can use as a universal hash family. It's important to note that the description of a hash function is just the description of A, and that's just log of u, right? Which is like, r times log of m. So this is an exponential improvement over a completely random hash function, which is ordered linear in u. Here it is linear in log u. So it's easy to sample. I just need to sample a key, right? I'm already working with keys, right? So keys are not too big. And it's easy to evaluate. We're only left to check, does this function satisfy the universal property? So let's check that. This is a simple computation. So claim the inner product hash family is universal. Okay, so we can do it by direct computation. We need to check that for any two distinct keys, if we pick a hash function at random from the family, the probability that the two will be mapped to the same slot is at most 1 over m. So fix distinct, let's call it k and k tilde in u. Now, the probability over A that HA of k equals HA of k tilde, that is the quantity that we want to show is at most 1 over m. Okay, so we have the description of a hash function. We know what it is, so just open it up. So this is the same product between A and K in A and K tilde are equal to one another for a random A. And here, now we need to start using the assumption that K and K tilde are distinct. And the fact that they're distinct, it means that there exists some coordinate at which they differ. Right? Both of these are vectors of r coordinates. If they're distinct, they must differ at some coordinate. So there exists some t in r such that the tth coordinate of the two vectors are different. So we're going to use this fact here. We're going to we can write these two inner products as sums, right? Going from I equals 1 to r of AI ki equals I equals 1 to r AI k tilde I. And I can move on one side only the tth coordinates, and I leave on the other side all other coordinates. So here I can write a t times kt minus k tilde t. So I moved on this side the tth coordinates of both vectors multiplied by the same coefficient at. And on the other side, I have the sum for I not equal to t of ai k tilde I minus ki. Okay, so let's see. Now, by assumption, we know that these two are different, so we know that this is not equal to 0. So because it's not equal to 0, we can divide out by that. And we're asking what is the probability that AT equals this ratio. So let's think about it. K and K tilde are fixed. We can also fix all the coordinates of A except AT. All right? So we're asking what is the probability that AT, which is a random number between 0 and m minus 1, equals this thing. Now this thing is something, and the probability that it equals specifically this one is 1 over m. because this has n possible values, but it is one of them. This has n possible values. It is random after fixing everything else. And so this is 1 over m. So this tells us that this hash family is universal. Okay? Okay, so we've learned that universal hash functions are not too hard to construct. They come from inner products. They're nice and explicit, easy to evaluate. So this lets us instantiate the solution we have so far. Now, we want to come back to another loose end that we kind of need to somehow fix. We would like to improve our solution and achieve a data structure or linear space, but now we want the time to answer a search query to be constant, not in expectation, but in the worst case. Okay? So here comes a very beautiful idea that goes by the name of perfect hashing. And roughly, it is basically saying, okay, let's continue using universal hash functions. Let's continue using this paradigm, but let's not use these linked lists. We're going to do 2 layers of hashing. So the data structure that we have in mind is going to look like this. So as before, we have all possible keys, and we are only specifically interested in certain number of n keys. First, there's going to be, let's call it a 0th hash function that, like before, it maps u into some m. Okay, so here it is. 1, 2, up to m. And then also going to have, instead of just putting a linked list to resolve whatever collisions we have here, we're going to take the sublist of all the keys that happen here, and we're going to use another hash function. Let's call it, this is the hash function h1, that will resolve collisions by mapping them into another array. So that's h1, this is h2, up to, so we have a total of m plus 1 hash functions, 1 first level hash function and m second level hash functions. And we're going to build this data structure in such a way that all of these second layer arrays have no. Now we don't know yet how we're going to do it, but this is like our idea. Let's say, suppose we can construct a data structure that has this 2-layer. First, you have a first hash function that kind of more or less evenly spreads out keys in the first layer. In expectation, a constant per bucket, but some of them will going to get a super constant number. And then I'm going to further resolve with collisions, with another hash function that maps a small number of keys to a relatively large domain so that there are no collisions. Okay? Now, the size of the data structure is going to be the size of h0 plus the size of h1, plus the size of hm. Okay? And what we want is this to be order of n. So we're going to have to ensure that's the case. And however, something that now, this is kind of the technical difficulty, And however, the time for the search at this point, good in the worst case. Time of H0, Hj, the relevant one. Because if you're doing a search, you follow H0, you end up somewhere, you follow that hash function somewhere else, and that will, because there are no collisions, you either find something or nothing, okay? So this is going to be order 1 in the worst case. Worst case. So really, we are only left to demonstrate that such a data structure can actually be built to begin with. So let's specify how we're going to construct it. We're going to construct it probabilistically. So in polynomial time, we'll be able to construct this in expectation. So now we're going to specify how to sample the hashes. Okay, because once we have the hashes, we have data structure. So first, we're going to keep sampling H0 until we have a fairly even distribution in the first layer. Okay, so we're going to sample H0 from U to M, and then if a certain condition holds, doesn't hold, we're going to try again. So we're going to try to sum up the square of the collisions in each bucket. So we're going to call it Ci squared. So sample H0, see how many keys end up in bucket I. So Ci is going to be number of keys in bucket I according to H0. So we sample H0, we compute how many collisions there are in bucket I, we sum up their squares, and if this is greater than some constant, I don't know, mu times n, then try again. Okay? So we're going to just keep doing this loop until it is the case that if you sum the square of the collisions, you get something that is, I don't know, 100 times n as an integer. Otherwise, if we succeed, go to sample the next layer hash functions. So we're going to say for I equals 1 to m, we're going to sample Hj, okay? But now, remember that we need to try the second level arrays to have no collisions. So these Hj's, I'm going to map them not to a small domain, but to a rather large domain. So this is Hi, sorry. To a rather large domain. How large? I'm going to pick them to be Ci squared. Okay, so if I have C1 things here, I'm going to map them to an array that is C1 squared. It's like square that. Okay? And then we're going to say that if Hi has any collisions, then try again. So for each I, one at a time, we're going to say, okay, try to sample Hi and see what happens to the keys that were in this bucket. Is it the case that when you map them after sampling Hi to a very large domain, you get no collisions? If no collisions, next one. If you get some collision, you try to sample Hi again. So by definition, if we are able to finish this process, this gives us something that looks like this. Now, why do we have this funny condition? Well, it's because this funny condition ensures that this is going to be order of n, right? Because let's see. M is going to be order of n, okay? So H0 is going to be sort of size n. Each of the HIs is going to have a size, because we're picking them to output something in Ci squared. This one's going to have C1 squared, blah, 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 up to Cm squared. So if we want the description of the data structure, which is the sum of all these contributions, to be order of n, and m is already order of n, then definitely we need the sum of the squares to be linear. That's why we have this condition that if the sum of the squares is not linear, then we're going to sample again. So really, like, we know that if we're able to conclude this sampling procedure, then we have a data structure that is linear, has constant worst-case search time. We are only left to check that indeed we are able to do this sampling procedure. It will conclude. And this is what we want to do next. It's two rather simple computations. To basically, we need to check in expectation how many retries we need to do here and how many retries we need to do here. And then in expectation, we know that we can conclude this in a reasonable amount of time. So we're going to do that now. Well, let's maybe first check the second one. So let's compute. So we're going to study the second level sampling. What is the so fix an I. So we're going to a particular bucket because we're doing this sampling, for every I. Fix some I in M. What is the probability that HI maps 2 of the CI keys to the same bucket in the array of size Ci squared. Okay? What is this probability? Okay, well, by union bound, this is the sum of among all pairs of keys. So let's say K and K tilde in the first layer bucket I. Okay, so these are considered all pairs among the CI keys in bucket I, that the probability over HI, that HI equals HI of K equals HI of K tilde. Okay, so these are distinct. It's a distinct pair. Distinct pairs. Well, how many pairs are there? Well, there is going to be Ci choose 2. And the probability that distinct keys are mapped to the same one by HI is 1 over the domain size by the universality condition, which is Ci squared. So this is roughly a half. It's, at most a half, definitely. So this is saying that the probability that we succeed here in each try is a half. So in expectation, we're going to need to try this twice for each hash individually. Okay? I'm actually going to move this equation up here because I want the space for the other equation. So Ci choose 2, 1 over Ci squared, at most half. Okay. So here we have analyzed the second level sampling. for the first level sampling, really we need to understand what is the probability that this happens. We want to say that the probability that the sum of the squares of a number of, where the CIs are the number of keys in each bucket in the first level, that is more than linear, is small. Okay, well, let's compute first the expectation of that number. So let's compute the expectation of sum of CI squared from the sum going from 1 to m. Okay. So let's expand further. So this is the sum from 1 to m. Okay. What is CI squared? Well, CI is also the probability, or rather is an indicator for j equals 1 to n. So now we're looking at keys. This is the indicator that H0 will map key j specifically to bucket I, right? So this quantity, if you look at, if you sum up all the indicators, does the jth key map to bucket I, and you add them all up, that is the number of keys in bucket I, and I square that. Okay? So this is an equality. Once I expand, I'm going to get cross terms, but because these are indicators and a key can only map to one bucket, not multiple buckets, we actually get the expression that this is the indicator that H0 maps Kj, and also I'm going to sum over J prime. Okay, Kj maps to the same place as Kj prime, which is specifically location I. Okay, so now I expand, I get all the products. And now I can switch the sum. And if I take the sum across all i's, then I can combine all the indicators across all i's. I'm only asking what is the probability that H0 of Kj equals H0 of Kj prime, period, regardless of which I. So that is the sum for j and j prime, the indicator that H0 of Kj equals H0 of Kj prime, close parenthesis, and close parenthesis. Possible pairs of keys. Now, when the keys are the same, when you have j and j prime that equal one another, they're equal, then they definitely go to the same bucket. So the indicator is always 1. So here they are. Otherwise, we have distinct pairs of keys. And how many do we have them? We have n choose 2, because we have n keys in there. Or n choose 2. And for all the distinct pairs, the expectation of the indicator is the probability that an event happens. And by universality condition, because we're asking when do different keys map to the same bucket, that is exactly 1 over m. Okay? So this is saying that the expectation of a sum of the squares is order of n, right? Because we have n here plus n choose m, that's roughly n squared, but we have denominator, we have m, which is linear, so that is order of n. And now we're done, because if we know that the expectation is linear, then by Markov inequality, we know that the probability that it's much more than the expectation is small. So specifically, the probability that the sum of the squares is greater than, say, mu times n is at most the expectation of this quantity by Markov inequality divided by mu times n, okay? And because we know that the numerator is at most n, by choosing mu large enough, this can be made to be at most half, okay? And it's saying that, if mu is large enough, the probability that this condition is not satisfied is at most half, okay? Or rather, the probability that we repeat is at most half. So an expectation we only have to repeat twice. And so this concludes the construction of perfect hashing. Once again, to recapitulate, we sample H0, the first level hash, until the sum of the squares of the number of keys per bucket is linear. When that happens, we sample second level hash functions until each bucket gets kind of spread out without collisions into a domain that is squared the number of keys that we have per bucket. The description of the data structure is the sum of the square, is dominated by the sum of the squares. That's why we made sure it was linear. So overall, that's linear. And because in two levels of hashing, you have no collisions, then you have worst case time. And this is, should be a surprising construction because in expected time to construct a data structure, you obtain a data structure that has linear size and constant worst case search, which in particular beats binary search. Binary search actually, you can do significantly better. Okay, so this concludes the use of randomness, hash functions to construct dictionaries. These are called dictionaries.